Hello, this is Stephen Scholka, the immediate past chair for the Statistics Division and your host for today's webinar. This is a collaboration between the Stat Division and the Six Sigma Forum. This is one of several we've had in the Stat Division this year. This is the second time we've been able to collaborate with the Six Sigma Forum group and to have Scott Sterbenz present for us. The recordings will be available in about a week at both of our ASQ locations and also on the Stat Division YouTube channel. If you have questions about Scott's presentation, you can send me on your question icon or location on your menu, and I will ask Scott those questions when it's appropriate. If you have some technical issues, you can send me the message, the host. So if you have any other questions, reach out. But with that, I want to introduce Scott. Scott is a Six Sigma Master Black Belt at Ford Motor Company in Dearborn, Michigan. He's been there since 2001, and he is great at solving quality problems using DMAIC and DFSS tool sets. And Scott is a fantastic bowler, and you'll see an example of that in his presentation. He's a licensed professional engineer in the state of Michigan. He is a three-time ASQ Global Team Excellence Award finalist. He holds both a bachelor's and master's degree in mechanical engineering from Wayne State University in Detroit. And he is also an avid mountain biker and motorcyclist. So with that, I am going to turn the controls over to Scott and for his presentation on chi-square goodness of fit test.
All right, Stephen, thank you very much. I'm very excited to be here today and really enjoy teaming up with the Statistics Division on doing presentations like this. So I hope you enjoy it very much today. My goal is to show you the theory and some practical applications of the chi-square goodness of fit test. And it's my hope that you can take back to your places of work what you learned today and use those to augment your success. So I'm going to spend a couple minutes on history and theory of chi-square, both the distribution and the goodness of fit test. It's nothing too deep, it's just a couple of slides, and then we'll go into the practical examples. So where I want to start with a little bit of history. So we've got some of our superstars here in statistics and mathematics. And as I get started here, I am going to turn on my laser pointer so I can show some things. So I'm going to start with our German statistician, Friedrich Helmert. And in the late 1800s, he computed the distribution of the sample variance of a normal distribution. And that distribution was named after him. It was called the Helmholtz distribution. And then independently, in the early 1900s, you had an English statistician named Carl Pearson. He rediscovered the Helmholtz distribution while he was developing a goodness of fit test for categorical data. So since then, the distribution has been referred to as the chi-square because of his notation, his calculations, which was the Greek letter chi. And then about 20 years later, Sir Ronald Fisher published a family of chi-square distributions for other statistical methods. So this is where the chi-square distribution comes from. I want you to remember the wording from the Helmholtz distribution. So it's the distribution of sample variances of a normal distribution. So what does that mean? That means if I take random samples from a normal distribution and I square each individual value, then I can create a probability density function of that result. So logically, I want you to take a look at the green and yellow line, or actually the yellow line first. So the probability of getting a value close to 0 is actually quite high when you take one sample from this distribution. And the probability of getting values farther from 0 becomes increasingly smaller. That's because the standard normal has a large proportion of its values close to 0, and a small proportion as I get to the tails of the distribution. So this relationship is shown by the yellow line, and it also represents 1 degree of freedom. So now as I take more and more samples from the normal distribution, and I square them and I take the sum of those, now you have a different thing happening. You have the values getting close to 0 starting to decrease because your chances of getting multiple values from the standard normal that are close to 0 are getting smaller, and you're adding multiple terms together. And so you can see that from the different colored curves here, and those represent the different degrees of freedom. So all in total, this is known as the family of chi-square. Well, that's all great, you know, if you're a history buff or if you're a mathematician, but how do you really apply this? Well, the chi-square distributions can be used for goodness of fit when you have counts of attribute data that are classified into categories. So see, what happens is that when you have counts of categorical data, there's generally an expectation of how those counts are going to be split up between the categories. So the chi-square goodness of fit test is going to answer the question if the distribution of the data that you have in your hand, which we call the observed data, matches the distribution of what's expected. So for example, if I take a look at the coin and I wanted to see if that coin was fair, I toss the coin multiple times and tabulate the number of heads and tails. And then I would compare that to an expected distribution of 50-50 or 50-50 split. So what the chi-square goodness of fit test is telling me is if my data matches close enough to what is expected. If it does, then in this case, the coin is going to be deemed fair. And if it doesn't, then the coin is going to be deemed not fair. So you can see from a couple of the other examples here that you're not just limited to 2 categories as you are with the coin, so you can have multiple categories. And in addition, you don't have to have a uniform distribution of the categories as well. I'm not going to go into the math in that much detail, but basically this is how the chi-square goodness of fit test was derived. So suppose that I had a set of categories, all of different sizes. So what I can do is I can transform the category size into z-scores using the individual category size, the average category size, and the standard deviation of category sizes. Then, when I'm looking at the sizes of my categories compared to the average category size, I really don't care whether those category sizes are bigger or smaller than average. I just care that they're different than average. So what I mean by that is that if I have a negative z-score, it really doesn't mean anything different to me than a positive z-score. So to just analyze the magnitude of the differences, I can square everything, and that's what I'm showing in the bottom equation. The next step is simply using population parameters instead of sample parameters, so I make those substitutions up here, no issue. And then technically the z-score for each category is really a residual. And then if I sum everything across all the categories, now I'm getting a sum of my residuals. And then the final part, this is the equation that you're going to recognize for chi-square. I'm just using bases of the psychrometric principles to make some additional substitutions. So like I said, I didn't want to get into that too deep, but for those of you that wanted to understand it a little bit better, I thought it was some good introductory information. So now how do we run the chi-square goodness of fit test? So I want you to imagine that you have actual counts of categorical data that's in multiple categories, and that you expect that categorical data to be split up a certain way. So just like the examples I showed you a few slides ago with the coin or the roulette wheel. So you can use the chi-squared equation to calculate the total residuals for all of your categories, and this becomes your observed chi-square value. So it's essentially a measure of how far away your observed data is from your expected values. So as an example, if I have a coin toss and I do 100 tosses, I expect 50 of them to be heads and 50 of them to be tails. So what I can do for each category, heads and tails, is I can say if I had 47 heads and I had 53 tails, I would just take the difference for each category between the observed number of occurrences and the expected number of occurrences, and I square that, so 47 minus 50 squared, and then I would divide that by 50. So I would do that for the first category, and then I would do that for the second category. 53 minus 50 squared divided by 50, and then I sum the two together. So this chi-square statistic is going to tell me how far away my observed values were from my expected values. Once you've done that, what you're going to do is you're going to compare that observed chi-square value that you calculate here to a critical value that you're going to obtain from a statistical table. And I just show a small snippet of it here. The critical value is going to be based on the number of degrees of freedom that you have. So that'll be the number of categories minus 1. So in the case of a coin, you have 2 categories, heads and tails. You'd subtract 1 to get the degrees of freedom, so it would be 1. And then you look up your desired mathematical risk. In most cases, it's going to be 5%, so it would be this column over here. And then what you do is you take a look at the intersection of those to pick your critical value. So if the observed chi-square value exceeds the value in the table, we say that the observed distribution does not match the expected distribution. And if the chi-square value is less than the value in the table, then we say that the observed distribution matches the expected distribution. I don't want you to get caught up on my wording there. I know I didn't use the phrases null hypothesis and alternative hypothesis and failed, reject, and null and things like that. A lot of times when I present results of a chi-square test, especially to management that might not be that knowledgeable in statistics, I will use the phrase, the distributions are considered the same, or the distributions are not considered the same, depending on which hypothesis is more likely true. So now we're going to take a look at some practical examples. The first example is going to show you how to use the chi-square goodness of fit test when you have a theoretical expected distribution. And those of you that may have been exposed to chi-square before, a lot of people use dice as a great example, but they use a single-sided die. This example is going to use a two six-sided die. So this example is pretty entertaining. There's a wonderful game that was released by Mayfair Games. It's a very highly award-winning game, and it's called Catan. It's actually quite popular, especially with some of the younger folks in our industry. And if you haven't played this game, you should definitely give it a try. So in, in this game, each player assumes the role of a settler, and the goal is to acquire resources in order to build and develop their settlements. And if you accumulate a certain number of resources, it allows you to achieve goals and earn points. And then once you earn a set number of points, the first player to reach that threshold wins the game. Now, my wife and I bought this board game for our twin sons last Christmas, and we enjoyed the game so much we also purchased the Android version from the Google Play Store. And this allowed us to play the board game as a family, but also by ourselves when everybody wasn't in the mood to play. So this is what the game board looks like. The game starts with each player selecting 2 intersections on the board. So this, for instance, would be an intersection, or this would be an intersection. And that corresponds with 3 numbers that can be rolled with 2 standard dice. So during the game, when a specific number is rolled, any player that has a settlement touching that number is going to receive specific resources. So for an example, if let's say that the die comes up with 5, so I roll the 2 dice and I get a 1 and a 4 or a 2 and a 3. So I look at the places on the board where there's a 5. So there's 1 here and there's 1 down here. So in this case, this settlement is going to get a resource, and this settlement is going to get a resource because they touch this number 5. And then this settlement is going to get a resource because it touches this number 5. Now, in the Android version of the game, my wife absolutely insists that the computer rigs the rolls of the dice in order to benefit the computer players, preventing her from getting the resources she needs to earn points and win the game. So what I told her is I said, well, you know what? I kind of hear where you're coming from. So what we're going to do is we're going to test your theory. So we were going to analyze 10 games and use chi-square goodness of fit to see if the computer was indeed cheating. So to do this, we set up a data collection strategy where we took a screenshot at the beginning of each game and recorded which players received resources for each dice roll outcome. And the plan was to compare the distribution of dice rolls from the game to the theoretical distribution of dice rolls through the chi-square goodness of fit test. So I'm going to show you exactly how we did that. So here's a snapshot of the board at the beginning of the first game. So this table here on the right shows who benefits from each dice roll. So as an example, the computer players are red, yellow, and green. My wife is blue. So if a 4 is rolled, the red, yellow, and green players benefit, but the human player, or my wife in that case, does not benefit. If an 8 is rolled, yellow is benefited and blue is benefited. Okay, so that's how that's working. Now, a really neat feature of the game is that at the end, the game tallies the number of dice rolls as the game, you're having to tabulate everything manually. Now, I can also tabulate a table of theoretical dice outcomes using a simple table, which is shown on the right. I think most of us are pretty familiar with this. So in this example here, this distribution here of what actually happened is going to be my observed distribution of dice rolls. And then this over here is going to be used to construct my expected distribution, because this is a set amount of probability based on probability theory. So now I can translate my wife's practical question into a statistical question that matches the objective of the chi-square test. Does the observed distribution match the expected distribution? All right, so how do we go about doing this? So the first thing I do is I take the histogram and I convert it into a table. So this is the number of occurrences that happen for each of the 11 possible dice roll outcomes. And what I want you to notice here is that the total number of dice rolls in this game was 73. This number is going to come into importance a little bit later, so we need to remember that number, 73. The next thing I need to do is I need to translate the theoretical distribution into a tabular format. So essentially what I have to do is I have to ratio up the expected occurrences so that the total number of theoretical rolls matches the number of observed rolls, which was that magic number 73. So here's an example. If I wanted to do this for a roll of 2, a 2 should theoretically pop up 1 in 36 rolls, 1 out of every 36 rolls, which would be a probability of 2.78%. So if I then take 2.78% of 73, I get 2.03. So what that means is that in a game with 73 dice rolls, a 2 would come up 2.03 times. Now, you know and I know that we should get integer outcomes. However, we have to set it up this way out to a couple decimal places in order for the math to be accurate. So now what I can do is I can repeat that calculation for all of my 11 dice outcomes. So we all know that 7 is the most popular outcome at 16.67%, or about 1 in 6. And the expected occurrence in a 73 dice roll game would be the number 7 should come up 12.17 times. So I can check to make sure that I did the math right by adding up all of my expected occurrences to make sure that they add up to the same number as the observed occurrences. And then that's how I generate that table. Okay, so now I have a table of observed occurrences, which is from my histogram taken from a snapshot from the game. And now I have an expected distribution that I had to manipulate just a little bit so I could get the theoretical outcome. So now let's run the chi-square test. So what I do for each dice roll is I line up the number of observed occurrences, and I lined up the number of expected occurrences, and I just follow exactly the same equation that I showed you before. So in this case, my observed occurrences was 2. My expected occurrences was 2.03. I take that difference and square it, which is shown right down here. And then I divide that by the expected occurrences, 2.03. And once I figure out that square and that quotient, I get a value of 0.00044. So that's how you do it for one of your categories. Next, what we do is we do that for all of the categories. So remember, the chi-square is just a sum of all of your residuals for each category. That's all it's doing. So we're calculating this chi-square using this equation for each one of my 11 roll categories so that I can get a sum, which is going to be important, and that's my final chi-square statistic. So my final chi-square observed value is approximately 7.14. So what do I do with that number? Well, I have to find the critical value from my statistical table, which is what we've done before. So there are 11 possible dice outcome categories. So that means I have 10 degrees of freedom. And if I want to take 5% mathematical risk, I'm going to take the intersection of those two columns which gives me 18.31. That is my critical value. So the final step is I'm going to take my observed value, which is here, and I'm going to take my critical value, which is here, and I'm going to compare the two to each other. And remember the guideline. If the observed value is less than the critical value, then we're going to say, yeah, the distributions can be considered the same. So in other words, what I observed was the same as what is expected. If the observed value is greater than the critical value, then it's just the opposite. We're going to say that no, the distributions are too far away and the distributions are considered different from each other. So when we take a look at this result, it's very clear that my observed value is less than the critical value. So because the observed value is less than the critical value, we can say that the null is more likely true, and we can say that the distributions were the same, which means that the computer was not cheating. Okay, so that's the conclusion from game number 1. So I repeated that same study for all 10 games. So we looked at 10 games in a row, and you can see that in none of the 10 games did the observed chi-square value even come close to the critical value. So in all 10 cases, I was able to show that the computer was not cheating. So I really couldn't be that sympathetic to my wife. All I could say was, you know what, the statistics show the computer is really not cheating. So that's the first example that I wanted to show you. And like I said, that covers when you have a theoretical distribution that you can compare it to. But not all the times are we going to have a theoretical distribution to compare it to. Sometimes we're going to have an empirical distribution that we want to compare it to. And this is what we more likely run into in industry. And that's why I wanted to give you this second example. So in this example here, I have a foaming process that's used to manufacture instrument panels. And one of our suppliers had a 12% scrap rate, and it was in danger of shutting down one of our assembly plants. Now the scrap was coming from all 10 of their machines, because they have 10 different machines that produce these IPs for us. Now I did have my manager at the time, he called me and asked me to head over to that plant and conduct a designed experiment in order to reduce the scrap. Now, we all know with DOEs that your process should be stable and should be absent of special cause. So I wanted to make sure that that was actually the case before I would run any type of DOE on this. So let's take a look at how we looked at it. I asked the supplier to provide me with their last 3 days worth of scrap data for each machine, and also the number of parts produced off of each machine. So here are the 10 tools. These are the number of parts that came off of each tool. And then these were the number of parts that had some type of defect in them from each tool that separated out. Okay. Now what I want you to notice here is that the production numbers for each tool are not the same. So I want you to take a step back and think about this for a second. So if the production numbers for each tool are not equal, should I expect that the scrap numbers for each machine would be equal? Well, of course not. But how much do you want to bet that I had somebody in that room that came up to me and said machine number 5 was the worst machine because it had the most number of scrap parts? I'm sure we've all been in that situation before. But what I'm going to suggest is that the right way to look at it is like this. A machine that processes the most number of parts would also be expected to have the highest number of scrap parts, provided that all the machines were scrapping at an equal level. A machine that processes the least number of parts would be expected to have the least number of scrap parts with the same assumption of a similar scrap rate. So this allowed me to translate my question into a statistical question that matches the chi-square test. Does the distribution of observed scrap match the distribution of production? So there are a couple of important numbers we have to remember here. The total number of parts produced, 2234, and the total number of parts scrapped, which is 271. So let's see how we're going to develop our tables here. Because if you remember, we need a table of observed values. We need a table of expected values. Well, this table here is very clearly the observed values right here. These are going to be the observed values right here. But we have to come up with expected values. So here's how we do that. Okay, so what I can do is I can generate the percentage of total production from each machine. So as an example, tool number 1 produced 227 out of the 2,234 parts, which represented 10.16% of production. Therefore, I would expect that it would be responsible for approximately 10.16% of the total scrap. So if I then take 10.16% and multiplied it by the total number of scrap parts, which is 271, I get 27.54 parts, which represents 10.16% of the total scrap. So in other words, tool number 1 had 10.16% of the production. They should also have approximately 10.16% of the scrap, or 27.54 parts. So I then can do that for all of the rest of the machines. So as an example, machine number 5 had 11.1% of the production. So if I take 11.1% of 271, I'm going to get 29.96. So this is how I get my table of expected values. It's based off of, in this case, the percentage of production. Now that I have those two values, observed and expected, lined up, pairwise, as I should in this type of table to run the chi-square, I can now calculate the chi-square score for each machine individually. So for example, in machine number 1, my observed number of scrap is 26. My expected scrap is 27.54. So I take that difference and square it, and then I divide by the expected value, which is 27.54. That's going to give me a chi-square value for the first machine of 0.09, as shown here. And then I can repeat that calculation for all the categories, because I want to remind you again, the chi-square is technically the residual from what is expected, and I want to sum those residuals over the entire number of tools that I have, and I do that, and my total chi-square is 23.41. Now I do the same thing as I did before. I go to my statistical table. I had 10 machines, so that gives me 9 degrees of freedom. I'm looking at 5% mathematical risk. Take the intersection of those two in my statistical table, that gives me a critical value of 16.92. So now I've got to compare those two values, what I calculated, what is the critical value, and that helps me make a decision. So here, again, I'm looking to see if this value, which is observed, is less than or greater than this value, which is my critical value. So if my observed value is less than the test statistic, then I'm going to say that the distributions can be considered the same, or the null is more likely true. If this value here for observed is greater than what my critical value is, then I'm going to say, you know what, the distributions are not likely the same, or the alternative hypothesis is more likely true. So clearly what you see here is my observed value is higher than my expected value. So what that says is that the scrap rates are different from the production rates, and therefore they're a special cause. If this were not the case, and the scrap rates were the same as the production rates, then there would be no special cause. Okay, so that's what we see here. We see here that at least one machine has a different scrap rate than what is suggested by its production rate. In other words, there's clear evidence of special cause. Now, clearly, while I have a scrap problem on all my machines, or common cause, I do also have special cause on at least one machine. So therefore, if I were to blindly proceed with a DOE without knowing that I had this special cause, I could make some very dangerous and wrong decisions. So it was a good thing that I ran this first, brought it back to my manager and said, you know what, I got to fix the special cause first, and then I can address the common cause with the DOE secondary. Now, one of the things that's really neat about the chi-square results is I can go back to my data table and I can figure out which machines caused the goodness of fit test to trip. So think about it this way. The observed chi-square value is the sum of the individual category chi-square scores. So if I take the critical chi-square value and divide it by the number of categories that I had, that gives me a pseudo-critical, in air quotes, chi-square value for each category. So therefore, if the observed chi-square score for any category exceeds this pseudo-critical value, that category influenced the results of the chi-square test. So in this example, the critical value was 16.92. I divide that by 10 machines and I get 1.692. So now what I can do is I can look through my table and I can see which tools had a chi-square value that was higher than 1.692, because then that unfairly influenced the test. So if I do that, I say my worst offender here is at 13.06, and then I compare the expected and the observed results, and I can say, you know what, this was worse than expected. This is my worst of the worst machine. And then I can continue to go down the level and I find, okay, this one is the same, observed is worse than expected. This is the next one here at 2.3, and I can see that my observed was much better than my expected, so this is my best of the best. Now I have a natural contrast between the best of the best and the worst of the worst, and this can help me identify what the special cause was. Now, just to kind of finish up the story, we did figure out what the special cause was between the machines. We fixed that, and then we reran the chi-square test, and everything came back as it should. All the scrap rates matched the production rates. We then ran a designed experiment, and we were able to get the supplier down to less than 0.1% scrap after that designed experiment. So this was a very, very successful project, and it was partly because we understood the existence of special cause before we moved into the DOE. All right, the last example that I'm going to go into is the most complicated example of the three. And this is where we're going to keep the promise that Stephen told you before, where I'm going to share a story about bowling. So one of the things that I do outside of Ford Motor Company and ASQ is I'm a technical advisor to the United States Bowling Congress. So I help them with all their research projects, and I also help them set up test plans and data analysis methods for them to analyze everything that's involved with the sport. One of the things that we study is bowling pin scoreability. So just for a little bit of information here, modern bowling pins are manufactured with a maple core, and they have a surlyn or a plastic coating. And I show you actually the transition through the manufacturing process here in a picture down at the bottom. Each pin is about 15 inches tall, and they weigh about 3.5 pounds each. Now, some other not so well-known facts about bowling pins. I know it doesn't look like it from your vantage point, but the pins are set up in an equilateral triangle, and they're spaced 1 foot center to center approximately. The center line of the head pin, which is the frontmost pin in the rack, is 60 feet from the foul line. Now, there are 3 specific tests that a bowling pin must pass before it's deemed acceptable for use in certified play. And these tests are conducted in series. So the first test is what we call the threshold test. This is nothing more than checking the dimensionals and some other physical properties like diameters, weights, radius of gyration, wood moisture content, coefficient of restitution, things like that. The second test is laboratory scoreability. That's going to be the subject of this presentation. And then the third test is a field scoreability and durability test. Now, for the laboratory scoreability test, we use a device called BowlScore, and I'm going to show you some pictures and a video of that in just a second. BowlScore allows the Bowling Congress to roll a standard ball into a set of 10 pins at a constant velocity, and it allows us to simultaneously control the entry angle into the pins and the offset of the ball's impact from the center line of the head pin. So we can vary the entry angle from 0 to 10 degrees by each degree, and then we can control the offset from the center line of the head pin to plus or minus 5.5 inches, and this allows us to assess the full range of expected ball impacts with the pins that are meaningful to scoring. So here's a picture of BowlScore. In this photo, the pins here are in the rack closest to us, and then we have the ramp for ball delivery that's shown over here. This dark brown plate that you see on the floor allows us to adjust the entry angle and also the offset into the pins. This is a view of BowlScore from the other direction. So again, here you can see some of the pins down here on the pin deck. This is the ramp, and then this here is another view of that plate over here. So what's really cool is not only the system is completely automated. So we've got an automatic pin setter, an automatic ball return, and the BowlScore system automatically adjusts the entry angle and the offset of the table to collect precisely the number of shots for each combination we desire. So a complete test is comprised of about 2,500 shots, which you'll see in just a second. And we can complete it in just a couple hours. So the pictures are great, but it's always better to see some type of video. So I'm going to attempt to play the video here for you. Bowl score works. Okay, so that is a video of how bowl score works. I hope that that came across in the presentation rather good. If not, when the presentation becomes available, you should be able to see it. Okay, so in that case, you can see we had a little bit of an entry angle into the pins, and then the offset was just a little bit off from the center line of the head pin. Now, before I get into how we analyze the bowl score data, I do need to make a couple comments on entry angle. So entry angle is the angle that the ball enters the pins and is measured parallel to the lane. And entry angle is one of the most important factors when it comes to scoring in bowling. So hitting the pocket, which is between the 1 and 3 pins for a right-hander, is only half the battle. And as you can see from this graph here, the strike percentage, which is on the y-axis, is highly dependent on the offset from the center line of the head pin, and it's also highly dependent on the entry angle. So you can see that as the entry angle grows, you can see that the strike percentages across most offsets from the head pin is greater than 4 degrees, which is also greater than 2 degrees. So the more angle of entry that a bowler can generate, the better their scores typically are. Now, if you watch a person bowling on TV, you might think that the professionals are generating like a 30-degree entry angle, but I can assure you it's only an optical illusion. A lane is 60 feet long, but only 39 inches wide. And so as long as a lane is conditioned as regulated under the Bowling Congress, even professionals that hook the ball the most are only generating about 7 or 8 degrees. And just by the way, we found that entry angles that are greater than that actually are detrimental to scoring. So to show you this example, I've got 2 videos here that I want to play. That's going to show you the difference between the entry angle of 2 degrees and 4 degrees. You'll have to ignore the background music that's going on in one. But what I'm going to show you here is I'm going to advance the video, and this is how you can see it. So I'm looking where the ball is starting to go from right to left. And with this ball here on the left, that starts right here. And with the ball that is on the right, that right to left motion is beginning, all the way probably right. I just got to get it in the right spot, right about in this spot over here. So you can see that the ball is in the same position, left to right, but as far as from front to back, the difference in the length of the lane is significantly different. So one is going to generate about a 2-degree entry angle, the other is going to generate about a 4-degree entry angle. So I'll play those again so that you can see them. Okay, that's going to be a shallower entry angle. And then this one here is going to be a sharper entry angle. Okay, so hopefully you can see the difference. Okay, so now let's get on with how we do the data. So this is how we collect the data from bowl score. We throw 10 shots at each offset and angle combination. And so for each of the 11 angles, there are 230 shots. Then for each shot, the pin count is recorded. So we were interested in strikes, which is 10 counts, 9 counts, 8 counts, and 7 or less. The reason why we don't record lower counts is for 2 reasons. So first, the offsets that we use in the test guarantee the ball is going to hit the head pin. And secondly, it's a relatively rare occurrence to hit the head pin and score less than 7. So that's why we combine that all into one category. Now we do actually record the remaining pins, but they are used for a different analysis. So in order for us to evaluate scoreability, I mentioned that the comparison is done to a pin that's already been approved for certified play. We call this our control pin. So we have a very, very large data set on our control pin and bowl score. So therefore, this distribution is going to become our expected values. Okay, and then the counts that we observed with the proposed pin are going to become our observed values. So I want to remind you that at USBC or the Bowling Congress, we have shown very conclusively that entry angle into the pins very greatly affects scoring. So therefore, we're interested in the bowl score results at each entry angle and we want to make sure that scoring is neither augmented or diminished across all entry angles. So now that we have the data, what we can do is we can now phrase our question into a question that matches the chi-square goodness of fit test. That is, for any entry angle, does the distribution of pin counts for the proposed pin match the distribution of pin counts for the control pin? So let's look at the data for the control pin. So the data is calibrated or tabulated separately for each entry angle. So this is entry angle 0, and this is a count of the number of strikes, 9 counts, 8 counts, 7 or less. And then for entry angle 1, 2 degrees, 3 degrees, all the way up to 10 degrees. Now you'll notice here that we've got 2,760 total counts. That's because this is from 12 total bull score tests on our control pin. So our sample size is very high on the control pin. So what I can do is I can take each one of those values and I can divide it by 12 so I get the results that would be expected for one bull score test. So what I mean by that is that at an entry angle of 0, in a typical bull score test of 230 shots, 71.58 should be a strike, 81 should be a 9 count, 59 should be an 8 count, and then 18.42 should be 7 or less. And I can do that for all of my entry angles 0 through 10. This is an example of data from a proposed pin that we had recently at the Bowling Congress. So again, notice that the data is broken out by every entry angle, 0 through 10. So this table over here is my expected counts, because that's from the control pin. This table here is from my proposed pin or my actual test, so these are going to be my observed counts. And all I do is the same thing that I've done before, is I take each entry angle separately, and I take the observed results and I compare them to the expected results. So let's take a look. This is an example for the 2 degree entry angle. So for strikes, I had 89 observed, I expected 80.75, and I can use the equation right here, observed minus expected squared. So 89 minus 80.75 squared divided by 80.75, and that gives me a chi-square score for strikes at the 2 degree entry angle of 0.84. I do that for the other counts, 9 count, 8 count, 7 count, and I get a total chi-square score of 3.03, which is shown here. And I do the same thing I've done before. I go right to my chi-square table. So I use my degrees of freedom. So I have 4 pin count categories. That gives me 3 degrees of freedom. And at the Bowling Congress, we actually only believe in 1% statistical risk instead of 5%. So we use a critical chi-square score of 11.34. And now I compare the values. So for a 2 degree entry angle, I had an observed value of 3.03. I have a critical value of 11.34. And then I remember these are my comparisons that I'm making. If this value here is less than this value here, I say, you know what? They're the same. If this value here is greater than this value here, then I say, you know what? They're probably not the same. The distributions are different. So in this case here, I have my observed value is less than my critical value. So I can say, you know what? For the 2 degree entry angle, I can say that the pins score similarly. Whereas if my observed value were greater than the critical value, I would say, you know what? The control pin and this proposed pin, they score differently. So now what I can do is that was the result for the 2 degree entry angle. I now compile everything for all my entry angles because I have to pass on all entry angles. And if you take a look at this table, there are some entry angles where we don't have a passing test. So 3 degrees, 6 degrees, I'm sorry, 3 degrees, 5 degrees, 7 degrees, and 10 degrees, they fail the chi-square test. So with the proposed pin not passing all of the entry angles, we can say that the proposed pin does not pass the laboratory scoreability test and it will not proceed to the field scoreability test. Now, inevitably, we always get asked by the manufacturer of a failed pin whether the scoring of that pin was higher or lower than the control pin. Well, you know, from the last example that we can go back to the data table, you know, we can kind of see what's going on. So as an example, for typical and amateur and professional bowlers, entry angle into the pins is generally between 2 degrees and 6 degrees. So although there are players on both levels that generate angles into the pins higher and lower than that, that's a typical range, 2 to 6 degrees. So by looking at the strike counts are higher than expected for both 3 and 5 degrees, we can communicate to the manufacturer that for these angles, their pins will score higher than the control pin because the strikes are higher, the 9 and 7 counts are lower. It's just the opposite for the 7 and 10 degree entry angle, where you have the opposite, where the proposed pins will score lower than the control pin. That's because the 7 or less counts are higher than expected, whereas the strike counts are lower than expected. So that's an example of how we use the chi-square goodness of fit test within the Bowling Congress. And as I wrap this up, what I do want to say is that when you are looking at warranty data, especially for me, when I'm looking at warranty data, or I'm looking at any type of data where I have products coming off of multiple machines and I'm making an attribute assessment of either pass or fail or yes or no, the chi-square goodness of fit test does a really good job of telling you whether things are acting the way that they should without special cause, or whether things are acting in the way that they shouldn't, indicating that you do have special cause, and it helps you scope down your project or whatever quality issue that you're working on so that you can come to a solution faster. So those are all of the slides that I have prepared to present to you today. And Steve, I believe we've got about 13 or 14 minutes left for questions here at the end.
Well, thank you, Scott. That was a very thorough explanation of how to perform a chi-square analysis. So I've got 2 questions. Could a P-chart have helped you to see if one or more of the machines was different from the others?
So there are different ways that folks can assess data. So certainly chi-square goodness of fit is not the only way that that you could assess that. You can assess it multiple ways, and I believe that you could have gotten a similar assessment using that tool. Yes.
Okay. Second question, when would you use this chi-square analysis or Pearson, and when would you use the likelihood ratio chi-square?
Okay, so I believe that's a very good question. Steve, you might have to help me out with this one. Is the second test, is that a chi-square test for association? Is that what that is referring to?
I wish I could help you, Scott, but likelihood ratio chi-square could be an association one.
Yeah, that's what I believe. That's what I believe it is. So that's the way I'm going to answer the question. So what happens is that when you're looking at chi-square test for association, you're looking for dependency between 2 variables. So as an example, if I wanted to find out whether somebody's gender is related to how they vote political party-wise in an election. So in other words, if I wanted to find out, do a disproportionate number of women vote Democratic, do a disproportionate number of women vote Republican, do a disproportionate proportion of women vote independent. That's something that I can do with a chi-square test of dependency because I have 2 variables that I'm considering at the same time. With the chi-square goodness of fit that I've looked at here today that I've shown to you, that's really not the case. I'm only looking technically at 1 variable. So for instance, is my scrap rate dependent on, is my scrap rate different than a given distribution that I have? I'm only looking at 1 variable, which is the scrap rate. Whereas in the political example that I showed, you're actually taking a look at 2 variables. You're looking at the proportion of men versus women, and then you're looking at the proportion of Democrat versus Republican versus independent. So that's the difference between those 2 types of tests.
Okay, well, hopefully that answered the question. I have no other questions in front of me. If someone wishes to send one in the next minute or two, please do so. In the meantime, I'll.
Okay, well, we'll wait for that. I do want to. Yep. So I do want to remind everybody that the presentation will be made available so that you can look at it in more detail if you choose. And also, if you wanted to do some practice with the data sets, regardless of the software that you use, I use Minitab, for instance, but you can do the calculations in Excel and several other statistical packages. The first two examples, you'll be able to copy the data right out of the presentation. In the third one, there was really a little bit too much data to show on one screen, so you won't be able to run that one. So don't try it and get aggravated because it's not all there.
Yeah. Okay, thank you for that. And again, our intention is to post the slides on our two respective My ASQ sites. If you're not a member of either one of those groups, please join and you'll be able to see that plus other information and webinars and stuff like that. And as I shared with those attendees, the stat division does have a YouTube channel. I gave you the location of it. If you go there, besides this presentation, it will be other presentations we've done. Scott did one for us in the first part of the year, and so you'll be able to look at those at your leisure. Okay, so now I got a couple more questions.
Great.
So, question, aren't expected frequencies less than 5 supposed to be combined with adjacent cells?
Okay, so that's a very good question. If you remember, you've got the some assumptions that are made with chi-square, just as you do with some of the other use.
So I do not know. It's just me.
But
It was cutting out, or it was
5. You can even
So, unfortunately, Scott, the last couple of minutes you've been in and out, and it may be where you're located, and I can see that you're talking, but we can't hear you. So, unfortunately, I will attempt to answer it. Usually, there's a rule of thumb when it's less than 5 about combining cells, just like someone mentioned. That's kind of a rule of thumb, not hard and fast. I think looking at the analysis, you make certain judgments when to combine cells or not. And again, Scott,
as low as 4, but that is one of the reasons why we combine 7 for this. Did not have made. We're not here.
So Scott, we've been cutting off for the last couple of minutes. So I apologize for that. We were going well for most of the presentation. So let me wrap up, and maybe the audio will resolve itself. I had one more question, Scott, if you're there. I don't.
Okay, hopefully that was okay.
So I will again let you go, Scott, since we can't hear you. If you have questions for Scott, you can email them to us as the presenter, and I'll pass them on to Scott. And I'm going to stop the recording because we're having technical difficulties. So again, thank you for participating in the webinar, and I will send you an email now so that you can send it here. So let me just send you a message for those.
Okay, I am still. So Steve, I don't.
Okay, so we're difficulty. So I'm sending you my email. If you have questions for Scott, send them to me and I'll forward it on to Scott. Okay. And with that, I'm going to stop the recording.